Hello, welcome to another problem session. This is a very standard problem in circular motion, circular motion dynamics. So what it is a circular track. It's kind of like you've probably seen this kind of track where you shoot a ball and it goes in a circle, and maybe it comes around and goes off like that. So we're talking about not any point of the circle, but a particular point. The ball is here and going around. At that point, it has a velocity that direction, but speed is v. And it says if this v is less than vc, if less than vc, then falls off. V greater than vc we don't know, that's the one I'm trying to find out, continues. When v equals to vc, continues, but barely, right? Okay, so that's the situation. So it is some instant t, it's there, and because it's going, we're going to think about going, continuing. We're looking for this continuing. It is in a circular motion, and it has two kinds of accelerations. As you know, in circular motion, it has acceleration pointed towards the center. So, and then there's a acceleration because it's going to speed up just from the gravity. Then it's got tangential acceleration in that way. While it's coming, it's slowing down, and then it's going to speed up, right? So at this point, just after that, the acceleration is more than acceleration. V was at some point. So potentially, but the question is not about this tangential. I'm going to just leave that alone. I see there's a question about tangential acceleration at that very point, and we will come to address that in another video. But for this problem, because it just barely makes it, what it's saying is what the normal force will be. So if I blow this part up, so here is the track, and here is the ball. So this is the track, and here's the ball, and acceleration is this way, centripetal acceleration, and the ball is moving this way. Okay, so its magnitude is v square over, if the radius of this is r, if the radius of this thing is r, so this is v square over r. Okay, so we'll look at all the possible forces that can be in this direction, and we try to identify. One is, of course, gravity. Will have component vectors, but there will be a normal force here too from the track. And because we are talking about barely makes it, this is barely pushing. If there is has a higher than VC, then I will need a more acceleration, right? So at v equals to VC, acceleration is VC square over r. When v is greater than VC, acceleration will be v square over r greater than VC square over r. So I will need more acceleration to be on this side. So just the weight won't be enough. There will be normal also, but at this at the critical thing, Fn will be 0. Fn will be 0. This is the condition when the speed is equal to that critical speed. This is the main observation that you probably have to argue why the normal force have to be 0. When V is greater than Vc, Fn is not 0. Okay, so for part A, let's do the part A. Part A, there's only one force in that direction, mg. So if I take this as the y-axis, then mg is positive component, is equals to mvc square over r, and right away we see vc square equals to gr, which just tells me vc is speed, so I just take a plus root of gr since speed is positive. Since speed is positive, so just take a positive root. Okay, so this is an A, and the B is a situation like this, and so V at the top is greater than Vc. So now when I write down normal is this way, both are in the same direction. So besides mg, you also have normal. So you have Fn plus mg, both pointed down, and AC pointed down is mv, v at top is square over r. V at top is greater than Vc. And so I can solve this, and that will give me Fn. So Fn will depend on the mass. As you can see, it's not mg. Minus mg is just actually is m v square over r. Let's just write down the v square minus g. So that will be the answer. Okay, this is a simple problem, but let's just make sure you understood that at the critical moment, the normal from the track will be 0. You can say what normal is actually a reaction force. So normal is a reaction force, and something has to push. So normal reaction force for push. So normal is a reaction force. And if not pushing, a ball not pushing on track won't be pushing back. That's the logic. So this is something once you get that, then doing this F equals ma is very easy. And that also says that if the speed is greater, then of course it has to be pushing, then the track will push back. And so this is also kind of not that hard. Okay, I'll stop here. This is a long enough analysis for this problem. See you in another video. Bye.